Okay, so in this video we're going to talk a little bit about orbitals and electron configurations and how you would do them, as well as a little bit of the details about the orbitals. One thing to remember is that there are 4 different types of orbitals before we get into sort of the nitty-gritty details of this. There's the s, p orbitals, d orbitals, and f orbitals. One of the things to remember about these is that each orbital or each orbital subtype will hold 2 electrons. Okay, and so for the s orbital, which there's just one, it's a sphere. Again, remember you can look at any of these, just do a search on Google Images or look in your book. But a set of orbitals, there's only one type of s. So a set of s orbitals is just one orbital. P orbitals, however, there are 3. There's one in the x, one in the y, one in the z direction. D, there are 5. F, there are 7, and therefore the number of electrons at a given energy level, or n, okay, the principal quantum number. So for the 1s, you can hold 2 electrons as well for the 2s, the 3s, the 4s, etc. For the p, which starts at quantum number 2, level 2, you can hold 6 because there's 2 in each of those. A set of d orbitals can hold 10, a set of f orbitals can hold 14. We'll see in a little bit. That's the sort of layout of the periodic table. Therefore, you can look at the periodic table and pretty quickly figure out what you're looking at. Okay, so if we look at the arrangement of these orbitals, one of the important things is that in general s orbitals have a lower energy than p, which have a lower energy than d, which have a lower energy than the f. And if you look at it, this is going to be the order in which you fill. Okay, you're going to start at the lowest energy. The first electrons to go in are going to go in at the most stable, lowest energy, and that's down here, the 1s orbital. The next one up is the 2s. Okay, so 2 electrons in each one. So elements hydrogen and helium, which have 1 and 2 electrons respectively, are going to just put those electrons in the 1s orbital. As we move up to lithium with 3, it's going to start filling the 2s. Once those are filled, you're now going to go to the 2p, which is, you can see, the next highest, and then the 3s, and then the 3p. Now there's a little bit of an oddity here. The d's come in at 3 as well, but 4s is actually a lower energy level. And in a second when we go on the table, that'll be a lot easier to remember that way. Okay, and the 3d therefore fills after the 4s. So the reason of the order of filling that we're going to sort of deal with here, and the reason we're going to label these things, and they're not always going to be s in front of p is in front of d in front of f, has to do with what the actual energy levels of those orbitals are. So one handy way to remember this is if you write out that n equals 1 through n equals 7 down that way, you'll see right here that you would start with the 1s. That's the only orbital at n equals 1. N equals 2, you have a 2s and a 2p. Then you have a 3s, a 3p, a 3d. And at 4, you have a 4s, 4p, 4d, 4f, and so on and so forth. If you were to write this out in order, pretty simple like that, and draw diagonal arrows through it, you can see that you're going to go from 1s is the first one you fill. Then you come and you do 2s. And then the next one is the 2p followed by the 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, and so on and so forth. So this is sometimes a handy shortcut to be able to write it out quickly, draw the lines, and remember the order at which it goes. A little bit better way to do it, though, is using the periodic table, which we're going to look at next. So if you look at the periodic table, one of the key things to recognize is that the way that it's diagrammed, right, these first 2 columns here are really the s orbitals. And the reason for that is everything on the periodic table, remember, was arranged in terms of periodicity, sort of repeating order again and again, and it has to do with their chemical behavior and how they act. Right? All of the ones in the first column here all tend to form +1 ions. Well, if you take a look, that's because they all have 1s electrons. For hydrogen, it's 1s1, lithium, it's 2s1, and so on and so forth, potassium, sodium, etc. If you look at the middle section here, the transition metals, they're all in this D block. Okay, and that's the 3D, the 4D, the 5D, the 6D. And the P block is right here. You have 2P, 3P, 4P. The F's right here, okay, they insert right sort of after the partway into the 5D. The advantage of this system of knowing that it counts based on essentially the row that you're in on the periodic table is that the atomic number will tell you in what order to go. You just follow atomic numbers. So if you're doing electron configurations, you're going to start with 1s and do that. And then you do 2s, 2p, 3s, 3p, 4s, 3d, 4p. So you just follow from left to right across the rows up until you hit whatever element you're looking for. So if you were looking for the electron configuration of one of the elements that ends in the 4p here, you know that you're going to look at your table and say 1s, 2s, 2p, because I'm in row 2. Next is row 3. There's an s, and then there's a p. Then row 4, there's a 4s. Here's a d. We have to know that the first d is 3. That gets a little confusing, but we can do with that. And then 4p. And we end wherever you are. So that's simply, this is a handy chart to look at. I've also posted it up on our course page. You can look at any point in time. It's in the book and can be found in numerous other places online as well. So in the next bit, I'm going to go through a little bit how you solve a couple of these as examples.